All right, so some of the newer material coming from lesson 42. I think problems 104 to 113 going to be looking at. And let's have at it. Let's not waste any time here. So you're going to sketch f of x. It's a rational function, 3x plus 6 over x minus 5. And then we're going to answer these limit questions as x becomes a certain value. What are the y values in the table? Can we see some trends or maybe not? Let's find out. All right, so what are the immediate things that one sees here? Let's get a Cartesian coordinate system going. And the first thing that jumps out at me is the y-intercept. Put a 0 in for x, -6/5. We got a little anchor now. 0, comma, -6/5. I might have to move that in a moment, but hopefully not. And then we've got ourselves an x-intercept here, -2. So if that's 6/5, that's 1 unit. Yeah, I'm around here. So -2 gets me 0. And that is the only place. There's only one answer coming from the numerator. -2 gets me a 0, and there's only one way to make a fraction equal 0. 0 divided by any denominator other than 0 will get us 0. Why? Because division times 0 gets you 0. You can check that answer. So let's answer the limit of this function as x goes to infinity. Well, I don't think you have to think about, what number to use to get towards infinity. A calculator usually gives you a viewing window of -10 to 10, and we're going to positive infinity right now. So 10 gives us a feel for this, but certainly 100 gets us a better feel. 1,000 gets you a better feel. I like to throw in 1,000,000. If I throw in 1,000,000, I've got 3 million in the numerator plus some minuscule change in comparison. And I got 1,000,000 in the denominator minus, really, in comparison, negligible change. And I think I know what 3 million divided by 1 million is as a ratio. Yes, I really had a x minus 5, which is going up at 1 to 1. And if I step back 1,000,000 miles, I'm not going to see that change. And 3x plus 6, I'm not even going to see the 6 if I go back 1,000,000 miles. I'm going up at 3 times that rate. So how many times will this altitude fit into that altitude? I think 3 times if I drew it well. And this is really what L'Hopital sees, but that's another discussion entirely. So I can see the end behavior, y equals 3 on both sides. Because negative divided by a negative also gives me a positive. Well, I can begin to see what's going on here. Question is, what's this asymptotic behavior? I hope you say x equals 5. Now, I probably should have done numerical work over here prior to this work over here, because now it's much easier to answer the limit questions, and I wanted to work you a little harder. I wanted you to understand what it meant as x goes to 5 with a plus sign above that 5. Well, that means I'm creating a table. And let's say I want to get to 5, but I'm coming in from above. 10, 9, 8, 7, 6, 5.5, about 5.01. What would happen if I put 5.01 in for x? Well, I sure as heck would be close to 21 in the numerator. And I definitely would get I don't know how many zeros I put over there, but I'm getting a number like this into 21. Well, dividing by 10, move the decimal place over. Right now, the decimal place is there. Let's put a whole bunch of move over 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Wow, that number just got very, very big. Oh, yes, I am headed towards positive infinity. And what happens if I put in a number that gets towards 5, but from the other direction, like 4.999999? I get a sign change. And if I get a sign change, I'm not going to positive infinity anymore, I'm going to negative infinity. I think you can see all of that from where the camera is positioned. And in mathematics, if we're not going to the same trending y values, then we say that limit does not exist. All right, so let's say that this represents some object moving. Well, as we get to 5 o'clock in the afternoon, what's the transition from negative infinity to positive infinity? Certainly not continuous. Can't be at two places at the same time. And we aren't beaming you up. Scotty's not beaming you up, sorry. So we say that does not exist. All right, so there's a little practice. It's called a rational function. YouTube has tons and tons of those done. So you don't have to look at my work. You look at anybody's, get some practice. Sine of 11 pi over 6. And I think it's important that you recognize that that number, I did it on a calculator, is about, I think I did, maybe I estimated, I don't know. It's about 5.75 radius lengths. You're used to measuring triangles with degrees, but that's also an arc length of a circumference. So depending upon what the circumference distance is, it's the same thing as measuring with degrees, provided we make every circle a unit circle with a radius of 1. So over here, not too bad for rotator cuff problems, that is a radius of 1. I tried to draw a radius of 1, but I know 1 radius length translates into about 57.3 degrees, and I think it's useful knowing that. So what are the places on the circumference that are most important? Circumference is 2 pi r, and we're holding the radius at 1. It's about 6.28 radius lengths for 360 degrees. And I'm at 5.75. And I know this is 0. It comes back to 6.28. I know that this one is about 1.57 radius lengths. This one is very familiar, 3.14. This one is 4.71, I believe, if my memory holds well. And so where is 5.75? 5.75, I think it's probably right around there. It's almost a full radius length. More in this direction. So that means I'm about 0.57 in this direction. Now I'm just doing some estimating. Now let's cut to the chase. Let's actually take the steps that I hope a week from now you can take, and you're going to tell me minus 1/2. A week from now, I hope you're doing it in your mind's eye. How did I get that? Well, we started with a triangle that hopefully is very familiar, the 30, 60, 90. We talked about where the ratios came from in previous videos. That opposite 30 degrees. You have the smallest side of the 30, 60, 90. If I drew it as a 30, 60, 90 this way, then that's the smallest side. And it's opposite that 30-degree angle. Whereas this is now 60. The 60-degree angle is here in that representation. Okay. All right, let's get to it. We'll leave that triangle there. Pi, 3.14 circumference radius lengths in a unit circle. I'm going to divide it up into 6 parts. Good drawings get good answers. I didn't like that drawing. All right, boom, boom, boom. I like that one. And I like that one. And I like that one. Boom, boom, boom. There. That one. Boom. There's the triangle that I'm looking for right over here. One of these triangles. Right? Which one do I want? Well, I got to have how many of these chunks? Got ahead of myself there. 11. That means there's 1, 2, 3, 4, 5, 6 in the upper half. Then there's 6 more, taking me to 12 pi over 6. And so I need one of these triangles less, which puts me there. All right, that's the one we're after. And I hope I'm going to get rid of that arc length, which is about 0.52 in that direction. Minus 1/2, 1, √3/2. And I'm hoping everybody does remember √3/2, approximately 0.87. Okay, so what was the sine function? Opposite the reference angle, which is 30 degrees, opposite the 5.75 radius lengths. I need 5 of these radius lengths. There's 1, 2, 3, 3.14, 4.71, 5.75 radius lengths takes me there. So the answer, minus 1/2. Now we'll do the cosine of minus pi/6. Minus pi/6. Don't think we have to spend much time. Minus pi/6 is going back 30 degrees. Same triangle. We say that that's a coterminal location. These angles are coterminal. The buses are coming into the bus station from different locations at different times. But they park in the same spot. So what was the cosine of minus pi/6? √3/2. Now here's your cosine function. There's one period moving forward, and there's one period moving back. We went back 30 degrees. There you go. That's 90 degrees worth of change. There's your 30-degree cosine value, and I'm saying it's 0.87. Does it look like? Because cosine only has a width of 1, -1. My width is 1 at 0. My width is -1. Does it seem like this might be correct? I hope so. Hope so. But again, 4 days of practice makes a big difference. And I don't know what day you are. Some folks have had the 4 days of practice, have looked at this already for 4 days and are getting it right. Other folks in the class haven't considered it yet. Don't know why. 11 pi/4, that's our other triangle. That pi, 180 divided by 4, 45-degree reference angle. We've looked at that from a Pythagorean relationship. All right, we got √2/2 and √2/2 as ratios, and that's about 0.71, roughly 0.71. And what's 0.7 times 0.7? 0.49, which is about that and that. I hope you can see is getting close to that from a Pythagorean relationship standpoint. So where are we? 11 pi/4, pi, 180 degrees broken up into 4 parts. Every one of these angles is 45 degrees. That means we have 8 of them. If this is 0, 1, 2, so on and so forth, 8 pi/4, once around the circle, so that becomes 9, that becomes 10. This is our triangle, 11 pi/4, which is approximately 8.63 radius length, 6.28, add another 1.57, add some more, you're here, draw your right triangle from circumference to the axis, use your reference angle. We have a √2/2 for a height. We have a √2/2 for a width, but that width is negative. And now what do we want to do if we're looking for tangent? We take this unit circle and we do what? We leave it alone if it's 45, 45. Whenever it's 30, 60, 90, I like to double the size of the triangle, get rid of those fractions. For right now, I don't see any reason to. Just -1, height divided by width, sine divided by cosine, opposite divided by adjacent. Lots of different ways to think about that. And there's our unit circle practice for the day. And we'll do 3 more tomorrow. All right, what's the period of the function? Is that what I wanted? No, this is just solving on the unit circle. So let's get a unit circle. Cosine measures width. So we really have 2w minus 1 equals 0. So our width we want to be equal to a half. Well, that measures width in that direction and in that direction. And if I'm in a coordinate system, then this is the origin, or 0 for an x value. Over here, I have a width of 1. So over here, a width of 1 when x equals 0, because x stands for what? Give you a pause there. I think you got to know what you're solving for. You're solving for I just went 360 degrees, but I want that marker to stop when I get a width of a half. Width is 1 here. Over here, it's -1. Up and down, my widths are 0. If I draw a triangle straight up, it's got no width. Here's a triangle. That has width right there. What happens if I get a little closer? Okay, let's keep a look at that width. What happened to the width? It used to be over here. Now it's here. Oh, that width's getting smaller. And every time I draw one, it's getting smaller straight up and down. There's no width. So I guess the question is, where does the width equal a half? Well, if that width is 0 and that width is 1, I think I'm right in between. Oh, can you see the triangles? There's one of them. There's another. And the width is a half. I wonder what kind of triangle has a half for a smallest side. Hopefully you're starting to realize 30, 60, 90. And a good drawing, do you think that's a 30-degree angle or a 60-degree angle? I hope you're saying 60. So one of my answers is pi over 3 because we want that language system. That works better for modeling. We'll get into some modeling here in the next week or two. You already have done some, right? Temperatures, average temperature in a given year. We got to turn years into angles and then angles into ratios. So it's a two-step function. And where else do I have? Oh, here. Well, let's see, pi over 3. That's breaking this up into 3 parts. 1, 2, 3. And there's your 4th, and there's your 5th. Oh, 5 pi over 3. That also takes me to 1/2. If I do that triangle, then the width is a half. Okay, so cosine curve, 1 period, max to max, half occurs here, half occurs there, but this is measuring width. I know it's on a vertical axis, makes it a little more challenging, but that's a width of a half right there. My width's a half. Yeah, and that looks like it's happening right about there. And this is 90 degrees right here. I hope it looks like I'm doing one chunk of 60. And then over here, that's 270. I got another 60-degree angle. So what's the 60-degree angle there? It's going to be this one, 5 pi over 3. I didn't think I said that as well as I would like to, but it's all right. We got repetition in this class. We can come back at it again. So what's the period of this function? I can see it's 6 pi immediately. Because what's 6 pi divided by 3? 2 pi. So x is a line. And what are we trying to do with that? We're trying to match up values, which I plug in. Let's get rid of this for now. I'm just talking about y equals x. And what does that stand for? I think I asked a while ago. I never answered it. Angle. And your brain's probably working with degrees. That's fine. 6 pi, 3 times 360. What is that? 1080? That's 3 times around the circle. Yeah. So let's say that this is 2 pi, 6.28, and y equals x. Then that's 6.28. And it looks like the circumference of the circle is matching up exactly with this linear function. And that is the number it takes in this function to go once around. Right? But what happens if I divide by 3? Well, then this line is going up 1/3 as fast. So how long is it gonna take to get to 6.28? 6.28. Whoa, takes a whole different input. Takes a whole different input. Doesn't take 2 pi. Yeah, does this look like it's 3 times 6 pi as a distance? That means the sine function, when we're talking 2 pi, goes up to a height of 1. Right, that's your normal, period. That's this one. Right, that's how long it takes for period. I haven't changed these values yet, but I'm just talking about period. And then I need a whole lot more because I'm dividing by 3. That period before repetition just got a whole lot longer. So dividing by 3, let's say it takes you 6.28 seconds to move your hand up and down. It's going to take me 3 times that to get the same result because I'm working 1/3 as fast. Yep, I've worked with people, especially youngsters raking leaves. And sometimes we get a youngster that just hides behind a tree with a rake like this. And then somebody spots him and starts working again. He's working 1/3. It's going to take him 3 times as long if he's working on his own to get the job done. So, what's the quick way for finding 6 pi? The long route is to set the argument of the function, x equals 3 to 0 degrees or 0 radians. I'll put both language systems down as you're trying to learn how to speak both languages. And I want x over 3 to equal 360 degrees or 6.28. Let's do 2 pi. Let's do it exactly. 2 pi radius lengths. I'm really pushing radius lengths. Why? Because I've talked with students who have finished trig, don't know what a radian is. I want you to come out of this class knowing what a radian is. We're going to talk about it a long time. All right, so what's the shortcut? The multiplier. That's what that multiplier divided into 2 pi is going to get you your shortcut to the period. What was the multiplier? This could have been written as 10 sine 1/3 times x plus 2. So my multiplier was 1/3. How many times does 1/3 fit into 2 pi? 2 pi divided by 1/3, not taking any shortcuts here, is the same thing as 2 pi times 3 over 1. Okay, that's a quick way to get the period of a function. All right. And we'll take more time on the period in the next problem. So let's go sketch it now. I see, let's go back to the original. I see a sine function, positive sine function. I like to measure from 0. I can do that in this case. I know this is 6 pi over here, brings me back to a height of 2, right? That's the midline. And I'm going up 10 and down 10. So I'm going up to 12 and I'm going down to -8. So my range is y values less than or equal to 12, greater than or equal to -8. And I got a quick sketch with all kinds of symmetry. 3 pi is going to get me 2. 3 pi over 2 is going to get me 12. Let's see how that one works. Let's put 3 pi over 2 in here. 3 pi over 2. What's going to happen to the 3's? Cancel. Where's pi over 2? Pi over 2 is straight up. What's the height right there? I think it's 1. 10 times 1 plus 2, 12. Now we're looking at widths. Notice I said W of X over here. The other one was H over X. Yeah, width. This is to help you remember. In the unit circle, what's the cosine? That width. Okay, all right, so what do we want for period? I know the period's pi, just by looking at it, okay? 2x minus 6 equals 0. Why don't we go degrees? And 2x minus 6 equals 360. All right, so when is that true? That is true when x is 3. So I have a cosine curve. I'll make a 0 out of it. 3. 0 is over here, 0 degrees over here. So what is my width in the unit circle over here? What is that width? I hope you're saying 1, which is a max. And we're at a max. Headed back to a max. And I now know that pi is going to be my answer for the period. 3.14 units. All right, because when does this equal? It equals 2x equal, let's move the 6 over there. Let's divide by 2. Oh, yes. 3 plus 180 degrees. Yeah, why? Because if you double 180, gone around the circle once. But we'll put this in factored form. Okay, let's move the 2 out there. Let's put a plus 0 here just to highlight the fact that the argument is a linear function. Doesn't have to be linear, but most times it is. And this is getting what? What's in the bracket? Angles. I got to have angles. And if I want to work without a calculator, the 30, 60, 90s, and the 45s allow me to work without a calculator to get the language of trig down. All right, so what is the height? The midline is 2. That hasn't changed. I'm still going up 10 and going down 10. So the range is no different. Okay, but the period has changed. If you're going up, if the linear function is going up at a 2-to-1 ratio, then that means that you're running around that circle faster than I am. Doesn't make any sense. But increasing, doubling table values. If you double table values and you start here at 90 degrees and you double that angle, you're at 180. I think you're going around the circle faster. Inputs are coming at you quicker. Twice as fast, actually. All right, let's see if we can sketch this cubic quickly. Point of inflection. Supposed to know how to do that at this stage. Minus b over 3a. So I now know that x equals 2 is critical. So I'll put 2 in. That's 8. The next one should be minus 24 without looking. Now I'm looking. Yes, so that's a correct answer. Minus 4 plus 5. Let's do that in our head. Minus 16. Minus 4 plus 5. Sure looks like minus 20 plus 5 is minus 15. I can immediately see that 0 gets me 5. And I know my slope at that instant is negative 2. All right, I'm ready to graph this now. So 0 gets me 5. I'm going down at 2-to-1. That means I'm coming back up. I know that's the point of inflection, which is 2 gets me negative 15. Now let's get the rate of change there. C minus 3a h squared. I haven't seen if the camera's in the right place. Good. C minus 2 minus 3a is 1. That's no different than the quadratic, right? You're looking for the a value. Ax cubed, bx squared, cx, d. Got an extra letter in here. H, this is hk. The most important horizontal and the vertical that goes with it. K for constant. H. 2 squared. Now I can see minus 12, minus 2, minus 12. I'm going down at 14-to-1 at that instant, and that's a max. Maximum decline. I'm going down fastest there. All right. And if you wanted to check that from calculus, you take a derivative. That changes according to that. That changes according to that. That changes according to that. And if you put in a 2, we should get negative 14. So let's put 2 in. 12 minus 24 minus 2. There's your negative 14. And I hope you see a relationship there that makes some sense to you with what we've done thus far, right? That's a minimum. That's the vertex of a quadratic. All right, so what is the x value here that I've been looking for? It does have a local max. Do you remember how to find it? That x comes from h minus the square root of minus m over 3a. A little bit of memorization. So what is that h value? Well, we got that. Let's get some more room here. That's 2. Minus, this one over here would be plus. Slope minus 14. I'm going to do the opposite of that. Square root of 14 divided by 3. That's that x value. No calculus used. If I wanted to find that, I'd have to plug in, well, at the y-intercept, it's useful to plug 0 in to find the fact that I said we're going down at 2 to 1 there. That's what allowed me to do that. Well, you plug a 0 in here. Right, the rate of change of this cubic at 0 is -2. And the other videos we've done have prepared you for this moment. We've talked about how things change at 0 with these polynomials in many of the earlier lesson sets. So I'm just going to move on because I'm not going to hold you terribly responsible for this. This is new material. It's there to help you. The goal of this is to help you to learn to think mathematically. You know, you may be thinking just about a grade coming to the end of the semester. I'm hoping I can maybe convince you that it's more important to get the education at this stage, to think about these things so you get some more success in your future classes. All right, so not spending much time on these problems. Can you read that? Y varies directly as x. So if you put a 5 in for x, you get a 10 out for y. Right? 5, meant to plug it in. All right, so what do we learn from that? We learn what k is, the constant of proportionality. There it is. Now when I plug in a 6, I can see that y becomes 12. So 5 gets me 10, 6 gets me 12, 5 gets me 10. I hope you can see the doubling constant. All right, so let's get rid of that one. Some algebra 1 here. Hope you know how to read that. Y varies inversely as x. Same thing. We drop a 5 in to get a 10 out. We can see that this is 50. Right? 50 divided by 5 is 10. What happens when the x changes to 10? Looks like the y goes to 5. 5 gets you 10. 10 gets you 5. Sure seems like an inverse to me. Then how do you read the next one? I don't spend a lot of time on variation problems. All right, so I hope I'm going to say this properly. Y varies directly as x cubed and inversely as z squared. I've also heard it stated as y varies jointly as x cubed and inversely as z squared. And if somebody has a better way of saying it, please put it in the comments because I don't work with it that much. All right, we're going to approximate 12/5. Let's see if we can do that in our mind's eye. Let me get my, so I got 1.4, 2.5 minus 1.6. I think I'm going to get 0.9. I think that's what I'm going to get, but I'm not sure. Let's do the rules of logs. No, let's do it organically first. 12 over 5 is equal to 3 times 4 divided by 5. I know 3 is e to the 1.1. I know 4, so times e to the 0.7 squared, and I know 5 is e to the 1.6, and I can use those approximations locally on the e to the x graph. The further you get to the right or left, I think more error ensues. But right now, this is what I tried to do. 1.4 plus 1.1, I said 2.5, and then I'm subtracting 1.6, and that's 1.5. I like my answer. Now let's get it from the standpoint of rules of logarithms. All right, what am I seeing? I'm seeing, let's start from scratch. 12 divided by 5. There's one rule. Okay, notice the subtraction of 1.6. Right? ln of 12, that's a product. That's the ln of 4 plus the ln of 3. Maybe I should do it in the order I did it there. That's the ln of 3 times, which means I'm adding the ln of 4, and I'm subtracting the ln of 5. Now the ln of 4 is breaking up into writing this as the number 2, e to the 0.7, and then squaring. So that could become this. And then your final statement, let's make sure you can see this. Final statement, ln of 3 plus 2 ln of 2 minus ln of 5. And it has taken us 3 months to get here. Well, that's supposed to be a star. How can I draw a star like that? My God, I got to put these on the, right? I got to put those. When I see you do that right, I got to give you a star. Yeah, so exact answer right there for 12/5. Exact answer, approximation here. I think you need to have an approximation. I think you have to have a feel for that number in order to see the rules. So that's how we approached it. And we got another 3-4 weeks of practicing this. That I hope it means something to you by the end of that. If not, you come at it again in pre-cal. A lot of folks are kind of dodging it now because students don't get there, which is too bad. Sketch. All right, so you stop the video and move my chair. Get Renee back a little bit. Come on, Renee, you're closing in on us too much here. There we go. All right, see if you can answer all those questions. See if you can get the sketch. You pause the video, try them all. I'll just go after it. No x-intercept. That's what I see immediately. I am not crossing the x-axis. Not going to happen. There is no way that you can make this thing equal to 0. If you could, then 6 would equal 0 times x minus 5 because division on the left is multiplication on the right. And I am not one who believes that 6 equals 0. So there's no x-intercept. So if I see a graph and it cuts the x-axis, I know you don't know what you're looking at. X equals 5. You had that before. It's there again. I know if I put bigger and bigger and bigger numbers in, 6 divided by 1, 6 divided by 10, 6 divided by 100, 6 divided by 1,000, 6 divided by 10,000, I think I'm going to 0. And I think I'm coming to 0 from the positive direction. We call that asymptotic behavior. And I know that if I put numbers less than 5 into the denominator, I get a sign change. Which means that my y-intercept better be 0 something negative. Oh, negative 6/5. So this isn't drawn to scale too well. All right. Probably should have put that in first to get a real good sketch. You know, that probably should have been here if that's 5 units. But that's okay. I think we can answer these questions now pretty quickly and easily. What happens as I move from 5 to the right? Positive infinity. What happens as I move 5 to the left? Negative infinity. Table values are heading there. What is the limit as x goes to 5? I hope you remembered from problem number 1. Does not exist. Hopefully that repetition helps. And now we're going to do entry-level derivatives. Why? Because we can. All right, so we're going to find the vertex and the y-intercept by taking q prime. Q for quadratic. Quadratic. Four-sided figures. Most important one, the square. How do squares change? Previous videos, the length of side of the square, 2x. So, rate of change, 2x times 2, 4x minus 20. Those don't change. When does that equal 0? At x equals 5, I get a slope that is 0. I plug 5 back in. I get minus 100, cut in half, minus 50 plus 7, minus 43. Taking the shortcuts now. I already knew that I'm going down at 20 to 1. It's on this side. Going down at 20 to 1 at 0,7. Okay. How did I know it's cup-shaped buff? The derivative of this is 4, which means that at 6, I'm going up at 4 to 1. At 7, I'm going up at 8 to 1. How long would it take for this to go from minus 43, from 5 to get to minus 20 as a slope? Well, 0, 1 gets me going down at 4 to 1, 8 to 1, 12 to 1, 16 to 1. Oh, I got to get to the number 5 to be going down at 20 to 1. Yeah. Or 20 units of change in the slopes. Awkward statement on my part. That's why I like repetition. I'm going to start talking about this more in the last few weeks. All right, so that's just a little calculus. Now, how would we have done all of this without calculus? We would have done, well, remember ax squared plus bx plus c, right? And we can talk about the slope 2ax plus b equaling 0, doubling that number times x, plus the constant rate of change. When's that equal to 0? When x equals minus b over 2a. Okay, minus b, 20 over 2 times a, 4. Okay, well, there's 5. I think it's easier to see this. Right? In my mind's eye, I'm going to look at, a problem like this. 3x squared minus 6x plus 12. All right, well, I'm seeing 6x minus 6 pretty quickly. I'm seeing x equals 1. That might be quicker than minus b over 2a. Minus b, 6 over 2 times 3. There it is. Right? Just another perspective. And I think it's a perspective that we want to talk about. We want to talk about the change in a square, a 3 by 3, many times until you see it. 3 by 3 gets you 9. What does 3.001 times 3.001 get you? 9.006001. I think I'm seeing a 6 to 1 ratio of change over a very small, that's an algebra 1 concept. And how does the number 6 compare to 3? I think it's twice that amount. Okay, so we're talking getting you ready for future classes. And in order to do that, I strongly suggest that in the middle of a pre-cal or a class like this, that you look at the video, the relationship between differentiation and integration, and also the geometric view of integration. I think those concepts might be in a semester model. Just might be too much to figure out what's going on and why. And if you don't look at the geometry, I don't think you got a prayer. Some students can. Some students are just gifted. And some of those things come to them, I guess. I don't know. But for the average person, I know how long it took me to see what was going on here. All right. So I think before you get to calc, if you're going to be forced to take a calculus class, in my day, not many people got to take calculus. Now, a lot of people take it, but the foundations don't support the study. And that's unfortunate. And that's why people drop out. Check the geometry out. Then you got a picture in your head as to what's going on, and then you can extrapolate to more difficult functions. That's just a piece of advice from somebody who's worked with this for a long period of time. And I hope you take that to heart. I hope you do check those out, because it's going to have a significant impact on your understanding of what's going on at the next level. And most people don't get that understanding, and that's when everybody drops out. This stuff comes at you from left and right, left field, right field. There is no sequential, excuse me. Let's start with linear. Let's go to quad. Linear function 1 minute, ln of x the next. You got to have some familiarity. Losing the voice, gonna sign off, and hope everybody has a good day.